assuming it's positive, I'll call this shear V just a little bit after the concentrated load, V plus. Okay. Then from the equilibrium, that means we have a beam here. I have a beam, and I create a cut here, and I create a cut here, right? And I'm looking at the portion of the beam which has the concentrated load, right? So I said, let's say the shear just before was V minus, just the shear after was V plus. Assuming everything is positive shear here means right face upward, left face downward. We have equilibrium, so what we have is that the upward forces, minus P going downward, minus V plus going downward, all this must be zero because the sum of all the forces must be zero. So we get from here that V plus minus V minus is equal to minus P. That means there is a jump, the shear after minus the shear before, the change of shear is equal to minus P. It means we must go in the minus direction. Okay? For example, in this example, let's show the equilibrium. Let's say if the shear here was negative 30 means it was going down, because positive shear would be upward for the right face. If this here is negative, it means on the left face it should be downward, but since it's negative it is 130 like this, and we have a downward force of 100. Clearly these forces are in equilibrium. 30, 100 and 130, they balance each other. Okay, we have equilibrium. That means it is correct to say whatever shear we had here, I would jump in the negative direction. But it comes also from this expression. I don't want you to remember expressions because in different books the expressions are different. For example, in some books it would say V plus minus V minus is plus P. But in these cases they have defined P going upward, okay? So they call it plus P, okay? So I don't want to remember like this. I want to remember that whatever load you see, if the load is pointing downward, you jump in the negative direction. If it's pointing upward, you jump in the positive direction. All right? All right. Now, exactly the same happens in the case where we have some concentrated, let's say 80, some concentrated axial load. Whenever we have a concentrated axial load, we must have a jump in the axial diagram. Okay, that means the axial force just before and just after must be different. Why? Let's look at the equilibrium of this little part. Let's make it in general for a force P. Let's say we have a force P here, right? Let's say the axial force before was N minus and the axial force after was N plus, two different values. Minus and plus doesn't mean one is negative, one is positive. It means before and after. Okay? So in this case, assuming again everything is positive, let's say assuming we have a positive axial force before, this must be tensile force, pulling, and we call it minus. Assuming this is also positive, this must be in this direction and positive, right? Pulling, tensile force on both faces. We must have equilibrium in the x direction, so what we have is that minus and minus plus P plus N plus must be equal to 0. So from here we get that N plus minus N minus is equal to minus P. So what we say is whenever I see a force pushing to the right, I jump in the negative direction, my diagram. So here in the diagram, if I was here and my axial load was already minus 60, for example, I will jump even more, I will go to minus 140 because I got this concentrated load of 80. Again, whenever I see something concentrated, I jump. It is instructional it is helpful from instructional point of view to start with this because this is very easy because you visualize it goes down, you go down, right? But here you see right or left, so you don't know right and left, does it correspond to up or down, right? So how do we think in general, not only for axial, not only for shear force, but also for bending moment, how do we deal whenever we see a concentrated load? Whenever you have something concentrated, you jump. If I would have a concentrated couple applied at the point, it means I must jump, my moment diagram must jump at this point. But how do I know? How do I know when I see a load, a 50 kilonewton meter here, and I have the moment diagram. Let's say the moment diagram was like this at this point. At this point, I know I need to jump. But how do I know if I jump in this direction or if I jump in this direction? How do we know in which direction we jump? That's the important question. So the rule is easy summarized as follows. We just look what the particular load, this load or this load or this moment, what does it do on the right face? Okay, for example, on the right face, such a load going down, it's a negative shear. So you jump in the negative direction. If you have an axial load which is to the right, on the right face, such a load would be a compressive load, which is a negative load. It means you must jump in the negative direction. Okay? You don't follow up and down because this goes right and left, right? But you know you must change your diagram. How do you know if you have to change upward or downward? You see this type of load on the right face, it is negative. So I'm going to jump in the negative direction. For example, this moment, will I jump my moment diagram, if this was 50, if the value before was plus 85, what will it be after? Will it be 85 plus 51, 35, or will it be 35? Okay? We check. Such a moment on the right face is pulling the top side, compressing the bottom side, right? It is pulling the top, pushing the bottom. So it is negative. So we are going to go here. If we were here, the next value will be plus 35. We will jump in the negative direction. Okay? This is very important rule, okay? I don't want you to get confused whenever you see something concentrated, or as we're going to see, when you're going to see something distributed too, you need to know in which direction to move, right? In the positive or in the negative direction. All right. So, concentrated things create discontinuities, create a jump, create a concentrated change, right? A very focused change, right? Sudden change, either in the shear force or in the axial force or in the bending moment. We're going to see here that in which direction we move, okay? All right. So this is true for everything. The next thing, so we know how to, whenever we see something concentrated, we know what to do. The next thing is, when we have something, let's say W of X, some distributed load, what happens to the shear if we have distributed load, right? And we have shown that in this case, again, because the force is pushing us down, we start losing shear. The same way like this, we lose shear, okay? The shear is decreasing, okay? And we're going to show this in a minute. If I want to show any formula, I just need to concentrate, take a small segment, and talk about this equilibrium. Then I can easily get the expression which governs this thing. Okay, so in this case, we showed that you don't have this sudden thing, you don't have a delta V, a sudden delta V, a change of V over zero length, right? Just before and after, discontinuity. But what you get is, you get a gradual change where the slope of the change is equal to, in this case, minus W of X. Okay, the slope of your shear diagram is equal to the intensity of the distributed load. The bigger the distributed load, the faster you move, up or down. Okay, if it's like this, it's going down. Okay, again, I just proved this for this simple case again, that if I have now a little length dx here, and if I had the shear here, let's say the shear here was V of X, let's say positive, that means on the right face upwards, then on this face, assuming again it's positive, it will be V of X plus dx. That means this is the section X, and this is X plus dx. So assuming positive shear here, assuming positive shear here, assuming this dx, and assuming that this is W of X. Now if this is small length, I can assume that this is constant over the small length equal to W of X. I cannot talk about the variation, right? Even this varies. I'm going to take a very small length here, then I can say that the intensity here is whatever W of x is. Right? So what we have is we have V of x going upward minus V of x plus dx going downward minus this total load, which is what? W of x times dx. All this must be 0. Okay? Equilibrium of the vertical forces. And from here we get that V of x plus dx minus V of x, if I bring this on this side, over dx is equal to W of x. If I take the limit when dx becomes smaller, then I can easily see that this is dV over dx. Okay, so the slope is equal to the distributed load. Okay. Okay. So what we're saying is the following. If I have some distributed load, let's say, which is, let's say I have this distributed load, let's say triangular distributed load, over some segment, right? And if I know that this load, for example, is 0, this intensity is 10 kilonewton per meter, and if I know that this was over a distance of 2 meters, okay, and if I know, for example, so this was, let's say, this, we are talking about some distributed load like this, right? Then, if I knew that the shear here, for example, before, I just plot the shear. Let's say the shear was plus 20. Nothing was happening, it was constant. Let's say this here and here. If there is no load, if there is no transverse load, no constant load, it will stay constant. If there is no distributed load, it will stay constant, right? Because if W of x from here, if W of x is 0, then the slope is 0, right? It will stay constant, it means, right? We cannot change. Indeed, if you have a segment here and there is no load over the segment, then from the equilibrium of the segment, this shear and this shear must be equal, right? We don't have a change of shear. So here we have a constant shear. So the question is, how does the diagram change between here and here? Let's try to calculate this, okay? All right, so clearly at this point, we start having loads pushing us down. We know that the slope of the shear diagram has to do with the intensity of this. The intensity of this here is 0, so it means we start with 0 slope. Okay? We have very small slope, so we start going down but with 0 slope, but as we go farther, this slope increases, right? And increase, let's increase this value also, let's make it 100, okay, because it's too small. Because otherwise I will still have to stay above and it doesn't. So let's say I will start losing, and then the intensity will be getting more and more and more, and the intensity basically, how quickly I drop, depends on how big this is. So this is clearly something which varies like in a parabolic way, right? Because the slope is proportional to this. The slope is linear, and when we integrate the slope, we get integral of a linear function. It's a quadratic function, okay? So we get something of this form. The question is, at the end, at this point, how do we know where we are? So whenever we have this type of formulas, whenever we have formula in this form, any formula which is written in differential way can be written also in an integral way. That means I could integrate here between 2 points. I could integrate between points 1 and 2. That means dv over dx times dx is equal to integral from point 1 to 2 to minus w of x dx. It will be, it's the same, right? But dx here cancels, so integral of dv. Integral of dv is v. Okay, so it means from here we get that the c at point 2 minus the c at point 1, when I integrate over 2 points, is the integral with a minus sign of w of x dx between these 2 points. So this form and these forms are equivalent, okay? They express the same thing in different ways. One in the form of a slope, one in the form of the actual change. Okay? So what it says is, if I have this section 1 and this section 2, and I want to compare the shear here compared to the shear here, the shear 2 minus the shear 1, the change of shear is equal to the integral to the area under the distributed load. Right? The area of the distributed load here is 100 times 2 over 2 is 100. So we lose 100 means, so we'll end up here at minus 80. And after that, if nothing happens, then we stay constant. Okay, it will be, the diagram will look something like this. All right? We have to understand that how to plot this, because you don't want to plot it like this. All right? Because like this would mean that you have a very big intensity here. You don't have. You start with zero intensity, so you start with zero slope, and then the slope increases, pushing you down all the time, stronger and stronger, until you reach the biggest slope here, and the total integral is this one. The change between here and here is the area under this, which is okay. So whenever we have distributed things, distributed loads, we know this is true also for axial loads. So when I have an axial load, for example, let's say we had loads over this, let's say this is 100, or let's say this is, I don't know, whatever, 5 meters. Let's say this intensity here is 20 kilonewton per meter, and it decreases to 0 in a linear way. That means the intensity looks like this. 20 kilonewton, here in the middle is 10 kilonewton, here it is 0, okay? It varies linearly, the intensity of this axial load, right? What am I going to say? Okay, the first thing is, we have to understand this type of load, what effect, first of all, we calculate the reactions. Okay, we have simply supported beam, the total load is 20 here, 0 here, so on the average it's 10 kilonewton per meter to the right, 20 kilonewton per meter here, 0 here, on the average, since it varies linearly, it's 10 kilonewton per meter, over 5 meters, so it means a total horizontal load of 50 kilonewton. That means this reaction here must be 50 kilonewton. Must be like this. Okay, and here we have a roller, we don't have any reaction. So when we calculate the reactions are like this, right? We plot the diagram, we come to plot the diagram, let's plot the diagram. We come here, this is the first point we encounter, and we see this big force. Big force means we have to jump in our diagram, right? Because we have this concentrated reaction, which is 50. Question is, in which way do we jump? Do we jump upward in the positive or in the negative direction? Well, we look what this force does on the right face. On the right face, it is a tensile force, therefore it's positive. Therefore, the starting value here is positive. Plus 50, we start our axial diagram. Our axial diagram starts with the value plus 50. Right? And after that, we drop. Do we go like this? Do we go like this? How do we go? Well, we have a very big intensity here. Right? First of all, do we drop or do we increase? Let's look at that. Well, this type of loads pushing to the right, clearly they are compressive, right? So they're negative. So we're going to move in the negative direction. Because we have a big intensity here, we're going to move fast here. And later we're going to move slower and slower, right? And I don't know where we are going to end up. If we're going to end up here, if we're going to end up here, let's see where we end up. How much we're going to lose? We're going to lose the area under the distributed load, which is 20 times 5 over 2. We're going to lose 50. So it means we're going to come exactly at this point at 0. So this is our diagram. We come at 0. It's a parabola. It's a parabola that goes like this. Right? We know that the expression is that dm over dx is equal to minus the distributed load in this case, because your distributed load was downward. Right? The expression, if I ask you what is the n of x here, n of x started with 20, and then it varied linearly to reach at 0, so it is minus 20 times x over 5. Because for x equal to 0, it will be 20. For x equal to 5, 20 minus 20 will be 0. So this is the correct expression for n of x. And therefore, because the slope is like this, I can write directly that the axial force at any point is the starting value, which was plus 50, minus the integral of this minus 20x plus 10x squared over 5. This is the expression which gives me the axial force at any point. That means from here I got that n2 is equal to the starting value minus the integral of n of x dx. This expression. Okay. The axial force at any point is the starting value minus, because it was put in the right, the integral of this, that means minus 20x plus 10x squared over 5. Here we get the analytical expression. Okay. Okay, this is what we said. All right, so we know how to do axial diagrams, we know how to do shear diagrams. Okay, it's very important we know how to do that. Okay. Now, the last important thing is to talk about moment diagram, which is actually the most important thing as we're going to see, because later when we calculate indeterminate beams, blah blah, having the correct moment diagram is the most important thing, because all the deflections and everything depend on the moment diagrams. Okay, so is that clear? Are we clear until here? Okay, so axial and shear diagrams behave exactly the same way. Concentrated load make us jump up or downward, depends what the load does on the right face. Okay. If we have distributed load, we have gradual change, not jumps, but a gradual change, where the slope, the bigger the intensity of the load, the bigger the slope. Okay? And if I want to find the change of shear or the change of axial force between 2 points, I just need to calculate the total area under the distributed load. Okay? Positive or negative, I just see the load, what it wants to do. That's going to on the right face. Okay? Alright, the last, and then we'll do examples after that to just refresh our memory. Alright. The last thing we talked about is how to construct moment diagrams, right? And we said the moment diagrams differ both from the axial and the shear diagrams. First of all, in the following sense. If I have no load, any kind of load within a segment, then the axial load stays constant. The shear load stays constant, right? Because we can change this only when we have axial or vertical distributed or concentrated loads, right? So if you have no load, nothing happens, right? Must be the same. That means if I take these 2 points, right, and there was no load on the beam, then if I had an axial load here, clearly this axial load should be the same, could not change. If I had here a positive shear here, here should also have a positive shear, and this from equilibrium should be the same. That means you have no load, nothing happens, okay? I mean, your diagrams stay constant, right? The axial and the shear diagram. But this is not the case for the case of bending moment. Because clearly, if you had here a moment, if you have here some shear V, because we said the shear didn't change, the axial force didn't change. If I had here some moment M, right, and here you have some length, let's say delta X, then the moment here cannot be the same as this moment. Why? Because when I take moments around this point, right, if these 2 moments were equal, if they were equal, then this segment would have a couple of forces and it could not be in equilibrium, right? Because you have V here and V here at the distance delta X, so you have an overturning moment. So if you have this shear here, then the moment here right? The moment on this side must be larger, right? Because you have this moment times over 10 plus v times dx, so this here must be m plus v times delta x, must be bigger than this moment. So if you have a positive shear, your bending moment must be increasing as you move to the right. All right? And we can see from here that the change of moment is this. So we can see that the change of moment over delta x should be equal to the shear in this case, okay, when you have this finite length example. So the change of moment over length is equal to the shear, okay? This is true if I would make this now a very small distance dx. This would be all still true, and you would have dm over dx is equal to the shear. And if you have shear, you have slope in your moment diagram. All right? So you have shear, you have slope. All right? Now, so this is the important thing. That the important thing is that dm over dx is equal to v. Okay, the distributed load. Okay. All right. So this is true. Even if I have a small segment and I have some, even if I have some distributed load, let's say W of x here, if I have a shear here, V of x, and here I have a shear V of x plus dx, both are positive, positive because on the right face, positive because on the left face, right? First of all, we know that this is not equal to this now in this case, a little bit different, okay? Now the important thing is if I have here a moment m of x, and here a moment m of x plus dx, right? We said that the change of moment, dm over dx, right? That means the moment at x plus dx, minus the moment at x over dx, the limit of this, limit, when dx goes to 0. The limit, this limit, okay, of dm over dx. Right? I say that it is still v of x. It is not affected by w of x. If there was no w of x, it is very easy to prove, right? Because if I don't have w of x, then this moment is this moment plus v of x dx. It's simply plus v of x dx, right? So when I divide the dx, it's v of x. But even if I have the distributed load, it's still the same. Let's prove this very quickly. Okay, let's take equilibrium of moments. Let's take, for example, all the moments around this point. So what do we have? We have minus m of x, this moment, minus v of x, this moment times the distance dx. Okay, this is a small length dx. So I can assume this is approximately constant, w of x. So the total load here coming down is how much? W of x times dx. This is the total load coming down. And the moment around this point is negative w of x dx, sorry, positive, in this direction. Positive w of x dx times the distance dx over 2. Right? The moment of this is 0 because it passed through here, plus the moment of m of x plus dx. All this must be 0. This is what we get if I write equilibrium of moments. So from here we get that m of x plus dx minus m of x. I move everything to the right hand side, so I get this is v of x dx plus w of x dx squared over 2. That's what I get. The change of moment is equal to this. I divide by dx both sides. I divide here by dx. That means I get rid of this, and this becomes without the square. And I take the limit when dx becomes very small. The limit when dx becomes very small is this becomes dm over dx. They change the slope. This becomes v of x. And when dx becomes very small, this guy vanishes. This is 0. Anyways, so we still get this same expression as before. that the slope of the moment diagram is the shear. It is not affected by the distributed load. Okay? It is affected by the distributed load indirectly because V of x keeps changing. Okay, so it has its effect, but at a particular point, the slope is equal to the shear. That's the important thing. Okay. So this is the only important relationship to talk about when we talk about moment diagrams. It is this. If I have positive shear, the moments must be increasing. That means this, if this was pulling the bottom, this will be pulling the bottom even more, because it must balance not only this, but it must balance also V of x dx. So positive shear causes the moments to increase. And of course, whenever we see a relationship like this, we can always integrate between 2 points. I can multiply this by dx. I can multiply here by dx. Integrate between 2 points 1 and 2. Dx and dx cancels. Integral of dm is m. So we get that the change of moments between 2 points is equal to the integral of the shear diagram. Okay, this is another way to write this expression in an integral form. Or to write, look, the moment at some point is whatever it was at some previous point plus the integral. So either I will talk about the difference, or we say that the moment was whatever it was plus the integral. Okay. So these are the important relations. Now, the critical point where we differ from most of the books of statics and many books of structural analysis too is the following. When we drew the axial diagram, when we drew the shear diagram, we always plot in a system of axes, right? Here's my x, right? And I plot the diagram. Positives are plotted up, negatives are plotted down, right? So if I have positive shear, I start with this value. If the shear goes down, I'll go down, whatever, right? We plot positive upwards, which is the regular way of having x and y axis, right? Okay, the important thing is, when we plot moment diagrams, okay, this is true for axial and shear. When we plot moment diagrams, it is not true. We will plot x like this, and we will plot positive for the moment diagrams. We'll plot positive downward. Okay, this is very important. If you look at your books of statics, they all plotted positive upward, and it's a big nonsense because once you try to apply this upward when you talk about frames, you get complete nonsense in your results. What we will achieve by doing this thing is the following. If we follow this convention to plot positive downward, then our diagrams will be always plotted on the tensile side as we want. We said we want to always plot our diagrams on the side with under tension, right? Okay, but we said, for example, when I have a simple support beam, right? Let's say with some load, right? We know that this beam wants to bend in this way, right? We know, for example, that the bottom side is under tension, right? Okay, because the bottom side, when you put this load, the bottom side is the side which wants to elongate. The bottom side is under tension. The bending moments here are positive, right? If I want to plot my moment diagram, which we are going to see is triangular, I want to plot it on the bottom side. So it's positive because it creates tension on the bottom side, and I plot it on the bottom side. The positive by definition is the one which pulls the bottom side, but I want to plot it then on the bottom side. So I plot positives, when I plot moment diagrams, I plot positive always on the bottom side, not on the top side. I don't use a right-handed coordinate system XY, I use a left-handed coordinate system X and Y when I plot the moment diagrams. This is very important. While when we plot the axial force and the shear forces, we use a right-handed coordinate system. This is a big difference. Okay, let's see now that we always end up with something consistent. Okay, for example, let's do this simple example. We have a beam of length L. Okay. We have a load of P. Draw the shear and bending moment diagram for this beam. Okay, P means we have a reaction here P over 2. We have a reaction here P over 2. We assume this is in the middle. Okay? So what does the shear diagram look like? We plot the shear diagram. We come here, this is the first point, we see a force. The force pushes us up, so we jump. We have a concentrated load, P over 2. We jump up. After this point, nothing happens. If nothing happens in the axial and shear diagram, we must stay constant. So we jumped up by P over 2, so this is a positive shear because we went upwards. At this point, we get pushed down. This is pushing us down. It's negative, or if you want, on the right face, this is a negative shear. Okay, so we must jump in the negative direction. We jump by P, so we end up at minus P over 2. From here on, nothing happens, so we stay constant. At this point, we get P over 2 pushing us up, and the diagram closes. The fact that it closes means we went as much up as we went down. It means we had as many loads pushing us up as down. That means we have equilibrium in the y direction. If the diagram doesn't close in the y direction, it means you don't satisfy the equation of equilibrium in the vertical direction. Okay? So one more time, very easy to construct this diagram, right? Up, constant, jump, constant. Now, when it comes to draw, this is your shear diagram. Okay? Now, when it comes to draw now the moment diagram, we come. First point we encounter is this. We know this point has zero bending moment because it was a pin. We know now that we have a positive shear, and we know the expression that dm over dx must be equal to the shear. That means since we have a positive shear, we must have a positive slope. Positive slope means moving towards the positive direction. Positive direction means down now for us. We said positive, we plot down. So we go down, and with a slope which depends on P over 2. And because it's constant, the shear is constant, it means our slope remains constant throughout. That means it's a straight line. And if I want to see how much this value, the slope here is P over 2. If I want to see where we'll end up, where is this point? The point is the area under the shear diagram. That means P over 2 times L over 2. That's PL over 4. The area under this area is P over 2 times L over 2, right? Is PL over 4. So we end up at PL over 4. After this point, we have a negative shear suddenly. It means we must be moving towards the negative direction. In the negative direction. Negative means upward for the moment diagram. So we move upward with a slope that remains also constant. And so we start losing bending moment, and over this area we are going to lose, in a constant slope, P over 2 times L over 2, we are going to lose PL over 4. That means at this point we'll end up at 0. And this is the diagram, and you see now, the way we plot the diagram, this were all positive values, it doesn't matter that we're positive. The important thing is, the diagram was plotted on this side. It means that the bottom of the beam was under tension, which is exactly what happens because we know this guy wants to bend in such a way. Right? Okay. Right? Okay. Okay. Let's do one more example. Now with a vertical beam. A column. We have this vertical column, and we have, let's say, let's do the case where we have, let's say, a load pushing a wind. Let's make the wind. Let's say constant intensity 10 kilonewton per meter. Let's say this distance is 4 meters. All right. Okay. Now, let's try to solve this problem to find, first of all, just tell me which is the side which is under tension, the left or the right? I mean, if this is a beam, right, this column, with this wind, which is the side under tension, this side or this side? The right one, this one, is under tension. Let's see, this wind blows it, it wants to bend. Right, left side clearly, right? The left side is the side which will be stretching, right? It has to be, so right? It bends under this type of loading, it wants to bend like this. Clearly, the left side is under tension. So, if we get everything right, our moment diagram should be something which is plotted on the left side, right? Because the side on which we plot tells us which, it's very important. The side, if we plot the diagram on this side, it means we need to put reinforcement on this side. We need to reinforce on this side. If you tell me the right side is under tension, we're going to put your reinforcement on the right side, right? Okay. So let's see. Let's come up with this. And I'm going to do that two different ways. One way, I'm going to look at the beam. Let's say the beam AB. I'm going to look at it like this, and one time I will look at it from B to A. Both ways are okay. Okay, let's do first of all from B to A. Let me do from B to A. Let's say we decide to look from here. Actually, in this case, it is easier to look from here to here because I don't need any starting values. I don't have any starting values. If I want to do from A to B, I need to calculate first of all the reactions. Okay? Let's do from B to A, and let's see what we say. So from B to A, I'll draw first the shear diagram, okay? From B to A, I come here, this is the first point. I don't have any concentrated load, so I don't jump. I am at 0 at this point, right? I don't have any shear yet. And I see load which is distributed 10 kilonewton per meter, pushing me up. So it means I must be going with a constant slope, I must be moving upward with a constant slope, right? Like this. This will be my shear diagram, right? And this will be positive values because I'm moving upwards, right? This. On the right face, such loads are upwards, right? So I'm moving in the positive direction. And if I want to write the expression for the shear as a function of x, let's say where x is this, right? I would say it's the starting value, which is 0, plus the integral of the distributed load, which is 10. So we say plus 10x. So it's 10x. This is the expression, 10x. So it means down here, the last value must be plus 40. This is what the diagram looks like when I look at it from here, right? Here, load pushing me up, constant intensity, so I'm moving with a constant slope until the expression is this, so it's 10x. The next thing is we come and want to plot the moment diagram now, okay? Again, I'm plotting, this is my x. Now, moment diagrams, I will not plot positive here, I will plot positive down, right? Because I'm looking at the beam like this, right? So, I start here, and I say, look, I don't have any applied moment, so I start from 0 for sure. I have shear, and the shear changes. The shear is positive. It means I must be moving in the positive direction. That means I must be moving in my positive direction, which is down for me, right? In this direction. And the intensity, the slope, must be proportional to these values. This value here is 0, so it means here I start with 0 slope. But a little bit later, it is something positive. And a little bit later, something more positive, and more positive, and more positive. So I get something where it increases the slope, right? It becomes more and more positive, so it means I move faster and faster in my positive direction, right? I call all these values, of course, all these values for me are positive, right? And what is the expression for m of x? What is the expression for m of x? is the starting value, which is 0, plus the integral of this. So it is plus 5x squared. For x equal to 4, is 5 times 16, it is plus 80, this last moment. Okay, 5x squared, when I put x equal to 4 meters, 5 times 4 squared, it is 5 times 16 is 80. Right, so this is the diagram. My diagram ended up being plotted on this side. The fact that it's plotted on this side means the left side of the beam is under tension. So I'm coming immediately and say, look, the left side is under tension, so I need to put the reinforcement clearly on this side. Okay? And of course, the bigger the moment, I'm going to put more and more and more reinforcement down here because I have bigger moments. I mean, this you're going to learn later in the course of reinforced concrete. How much reinforcement you need to put to pick up a certain moment. Okay? But the important thing for now, it is very important to understand that based on this diagram, based on the plot on this side, we know that we need to reinforce the left side of this column. Right? Let's say now that we change and I want to look at this beam this way. Not up to now, we looked from B to A, right? Now I'm going to look from A to B. Right, let's do that. This is a very useful exercise to do. Right? If I want to look from A to B, to plot anything, I need to know the starting values here, because here clearly we have some shear, we have some bending moment, we have some values, some reactions. So we need first of all to calculate the reactions here. Well, there is a total load here. This is a total load of 4 times 10, a total load of 40 here basically. I can substitute with the equivalent horizontal load. So clearly here there must be a reaction of 40 in this direction. Right? And taking moments around this point, clearly this wants to create an overturning moment of 40 times 2, 80, in this direction. So I must have a bending moment here of 80 kilonewton meter in this direction. One more time, taking moments around this point. This is minus 40 times 2, so this must be plus 40 times, plus 80. Okay, these are the reactions, so we need to calculate the reactions. I cannot plot in this way if I don't know the starting values. Okay, now we come and we are going to plot. Always we plot first the shear diagram, right? So I come here, I look at the beam from A to B, and I say, look, we come, this is the first point I see on the beam, and this point already has a concentrated load. This concentrated load pushes up, so I get a load of plus 40 here, pushing me up, plus 40, I call it plus 40, right? Because it pushed me on the right face, it is upward, okay, it's a positive shear load. And then, what do I see after that? Then I see little loads pushing me down, pushing me in this direction, pushing me down. So I start getting pushed down, and the slope, of course, is equal to the intensity. But the intensity is constant. It means I'm moving with a constant slope. And how do I know where I will end up? Well, I will calculate the area under this, which is 10 times 4 is 40. So I know that after 4 meters, I will lose 40, so I will end up here. So the actual diagram is going like this, all positive, like this. This is the shear diagram in this case. Okay, this is what I say. Right? Now, if you look at this diagram, we just plotted, and you look at this diagram we plotted before, we notice that one was plotted this side, one was plotted this side, but we don't care. We don't care when we look at shear diagrams or axial diagrams on which side we plotted. We only care about the sign. We care that this was positive shear, we care this was positive shear. We said already, the shear, if it's positive or negative, tells the whole story. Right? If it is positive, when I looked at it this way, when it's positive, it means right face upward, left face downward. When I had this result and I said positive, I said right face upward, left face downward. We agree, we don't disagree. We both say the same thing. We know in which sense it wants to shear. In this way, or in this way. We also know that a positive shear like this wants to create cracks, diagonal cracks, moving upward. So the cracks, I know if there's cracks here, they will be developing in this direction, upward, right? As I move to the right, upward. When I come from here, as I move to the right, upward, my cracks. It is uniquely determined in which way the cracks develop. So if I want to put reinforcement to take care of these cracks here, because, so if I want to, I know that the cracks won't develop in such a way. So if anything, I must put some reinforcement in this direction to close these cracks later. All right. Okay. Again, remember that such a crack would be very critical because it would make these two things separate. Right? If you would tell me the crack is in the opposite direction, then with this load, this crack doesn't separate, they still get pushed together, right? The crack closes, right? This is the crack that wants to develop under such load because it wants to make this thing fly away, right? If the crack would be in such a way, it is not really the worst crack you can develop. The cracks always develop in the worst possible way. They want to damage the structure. They don't want to say, good job, congratulations, right? They want to create damage. They want to create failure, okay? So they are created in such a way, but this is all predicted fully by the fact that you had positive shear. No matter how you look, you had positive shear. That means on the right face upward, on the right face upward, and cracks which develop upward, no matter how you look, like this, or upward, like this, right? Upward means as I look at it like this, it moves upward, like this. Upward means as I look at it like this, upward, like this, same. All right? Now so we disagreed how we plot the diagrams, but we definitely agreed on the sign, and that's the only thing we care. Now let's go and draw the moment diagram now. To plot the moment diagram, we start from here, right? So the first point we see is this point. This point. This point already has a concentrated load. Well, whenever we have a concentrated moment, we must jump in the diagram, right? So a moment which was in this direction doesn't pull the top or the bottom. This moment pulls the top and compresses the bottom. Right? Therefore, it is a negative moment. So I'm going to plot it, this 40, I must have a jump in the negative direction. I must jump to negative 40. Positive would be plotted down, negative is up. So I'm going to say negative 40 here. I'm going to put negative 40 up on this side. Because it was negative. Positive now, if positive, I'll plot on the bottom side. And for the moment diagrams, positive, I plot on the bottom. Okay, so it is like this, negative. And then, okay, so one way to look at it is like this. Another way to look at this is say, look, this type of moment is pulling the top, so it's clearly a negative moment. It pulls the top side, so it must be negative 40. No matter how you look at it, it's okay. Now, you are at negative 40, you have a positive shear. Positive shear means you must be moving in the positive direction. That means you must be moving in this direction. And you have a big shear, so you must be moving relatively fast. And a little bit later, because the shear decreases, the slope must be decreasing, right? So I don't know how it will go exactly. It might go like this, it might go like this. We'll see eventually that it will go like this and will come exactly at 0 here, okay? Right? But the important thing is first, intuitively, looking schematically or qualitatively, we can see we have a positive shear, so we must be moving in the positive direction with smaller and smaller slopes. So you have some curve that curves, right? It's not a straight line, right? And if I want to see how much moment I lost or I gained between here and here, is the area under this diagram. The area under this diagram is 40 times 4 over 2, it's 80. 40 times 4 over, this value was 80 and not 40. This bottom moment was 80, right? So this starting value was 80, right? So I said, we move with the big slopes, smaller. I will gain as much as the area under the shear diagram, which is 40 times 4 over 2 is 80, so I'll end up at 0 here. And at this point, actually, because the shear is 0, it means I come with 0 slope. I come with 0 slope, it's a parabola, like this. All these values, of course, are negative. The expression for the shear is minus 80, the starting value, plus the integral of the shear. The integral, okay, I didn't write the shear here. The shear V of x here was, the starting value was 40, minus, because we were losing, minus 10x. This was the expression for the shear. 40, and then we were losing 10. 40 minus 10x. The expression here was 0 plus 10x. But remember that this x and this x are different x's, right? This is actually, if you want, let's call this here x2, and this here let's call it x1, because I measure x1 here and x2 here. So this is 40, the starting value, minus 10x2. And here the moment, as a function of x2, is the starting value, which is minus 80, plus the integral of this, so plus 40 x2 minus 5x2 squared. This is the expression. When I plug x2 equal to 4, I will get 0. Now, when I look at this diagram and this diagram, they completely disagree on the sign. The values are the same, 80, 0, 0, whatever, right? The values are the same. But these are called positive, these are called negative, right? But both of them have been plotted on the same side. Both of them agree that the left side of the beam is under tension, right? Basically, what this guy said here, the negative 80, means that the top side is under tension, that's why it was negative, so the moment is like this. This guy here who said positive, who was looking at the beam like this, says the bottom side is under tension, so the moment is like this. Both agree on how the moment looks like. Both agree that the left side is under tension. But, of course, they disagree on the sign. But it's obvious it must disagree, because if this side is under tension, then this is the bottom side, so this should be positive. If this is the side under tension, then this is the top side, so it should be negative. Right? So, to make the long story short, it is important when we plot diagrams, okay, it doesn't matter how you are going to look at the beam, you can look like this anyway. You should know that if you look at it different ways, you end up, for the axial and shear diagram, you end up with diagrams plotted in opposite directions, but they agree on the sign. If you talk about moment diagrams, they disagree on the sign, because the one side for one guy is the bottom, and for the other guy is the top, right? So one guy will call it positive, one guy will call it negative, it's obvious. But they both agree on the side, that they both agree, for example, in this case, that the left side was under tension. Right? So this is very, very important to understand. All right? Okay. Now, what I want to show you so this of course was a quick review, but I'm going to do one example of doing, just to make sure we're all on page, and then I'm going to show you how we can construct very quickly the different diagrams. It's very important to be able to calculate quickly moment diagrams, because if it takes a long time to do the moment diagrams, then we'll be spending our time doing the moment diagrams instead of what we really want to do later in this course, which is calculating other things. Okay? Okay, actually, let me just say, so we have something new today. I will say something which is important, okay? All right. whenever I have two beams which have the same intermediate load here, so we assume we have two different beams, beam 1, beam 2. They have the same intermediate load, but they are not the same. The beams are not the same themselves. What do I mean by that? For example, let's say, I'll give an example, okay? I'll give you some examples. Let's say we have a simply supported beam with a uniform load, okay? Or, let's say I have a cantilever beam with a uniform load, okay? With the same uniform load. Or, let's say I have a cantilever beam like this with a uniform load, right? Okay. All right. Or, no more ors, okay? 3 cases. Okay, I'll do more ors later, okay, with more complicated examples. But let's say we have these 3 cases, okay? In these 3 cases, between 2 points, let's say between this point and this point, between this point and this point, the loading is exactly the same. What changes in this different case, for example, in these 3 cases, we have different supports. Okay, this was a simply supported case. So if I have this, for example, 10 kilonewton per meter, and this is, let's say, 4 meters, okay, then this here was 20 and 20, right? In this case, all the load was picked up here, 40, plus I had some bending moment, right? Here, all the load was here on this side, it was 40, and we had some bending moment in this direction. Okay, 40 times 2, this is 80, this is 80. Okay, so this is, I calculated the reaction. Three different beams, right? They all have different, the diagrams look different, okay? The different diagrams for these 3 cases are different, right? Let's see what they look like. Let's do for each of these cases. Let me do very quickly. These cases, we go up by 20, then we start losing 10 kilonewton per meter, and we end up at minus 20, then we get 20 upwards. So this is the shear diagram. Okay. So again, 20 we jump up, we get pushed gradually with constant slope. We lose between here and here, we lose 20 times 4. We go to minus 20, then we get the 20 that pushes up, and the diagram closes. Okay. In this case, for example, we go up by 40. We go to plus 40. Right? And then we get this load pushing us down. And after 10 meters, 4 meters again, we end up at 0 in this case. In this case, we start at 0, we get pushed down, we lose 40, right? Over the 4 meters. At this point, we get 40, and the diagram closes. Okay, this is minus 40 in this case. This was all minus, this was all plus. Here it was a little bit of plus, a little bit of minus. So this is the shear diagram. This is the shear diagram for these 3 cases, right? Okay. Okay. The important thing now. How do these diagrams differ? These diagrams differ only by a constant. That means if I take this value and I add everywhere plus 20, then this will become 40, this will become 20, this will become 0. I will get this diagram. If I want to go from here to here, I will subtract 20, then I will get this will become 0, this will become minus 40. They differ only by a constant. 2 diagrams differ only by a constant. Why? Why do they differ only by a constant? Because for any of these cases, the expression for the shear is the expression at point 1, let's say point 1 was this one, right? It's whatever the shear was at point 1, minus the integral of q of x dx, right? So the only difference, this term, q of x dx, was the same for any point. This integral was the same. So the only difference if I go to this case, or this case, was the difference of what the starting value was, right? So it's only different by a constant, these diagrams, right? They are basically the same, just shift it a little bit up or down. Alright? Just a little shifting will give you all the diagrams. Alright? Now let's do, however, also the bending moment diagrams now for these cases. For the first case. Okay, so here v of x in this case is 20 minus 10x. In this case, v of x is 40 minus 10x. In this case, v of x is minus 10x without anything in the beginning, right? I mean, they just differ by constant, right? Okay. Now, let's go here and plot the moment diagrams in this case. We start at 0 because we didn't have any moment. We have positive shear, so we must be moving in the positive direction with a big slope, but as we go to the right, the slope decreases. And at this point here, the slope becomes 0 in the middle. And after this point, we start having negative shear, so we must be going in the negative direction, so we must be going up. So it is easy to show actually that how much we move from here to here is the area under this diagram, okay, which is 20 times 2, 40 over 2 is 20, so this is plus 20. This is the maximum bending moment is 20. And then between here and here, we start losing, right? We have negative, we start moving in the negative direction. So again, 20 times 2, 40 over 2 is 20. So actually the expression for m of x, if you want, is the starting value, which was 0, plus the integral of this, so plus 20 minus 5x squared. And this is what 20x minus 5x squared. This is the expression for the moment. And if I put x equal to 4, you get 80 minus 5 times 16 minus 80 is 0. Okay, you go to 0. Okay, if you put 2, you will get 20. Okay, so this is for the first case. Let's do the second case. Second case was this case. We come here. We have a starting bending moment, which was what? 80, right? Positive or negative? On the right face, this pull in the top is negative. So I'm going to start with negative. I'll start here at negative 80. I'll call this a negative moment. And then I have positive shears, so I must be moving in the positive direction. At the beginning, fast, but as I go farther to the right, less and less and less sharp. And at the very end, I should come flat because the shear will be 0. So it's a curve that goes like this. I just don't know exactly where it will end up. But to see where it will end up, I know that between these 2 points, I will gain the area under the shear diagram. 40 times 4, 160 over 2 is 80. So from minus 80, I will get 80, so I'll come at 0. So the curve clearly is like this. And this is the curve. Let's write the expression for m of x. What will I write? The starting value, which was minus 80, plus the integral of the shear, plus 40x minus 5x squared, right? Let's do the last case. The last case, what will I say? I will say we are at 0. We didn't have any applied moment, so we start at 0. I have negative shear, so I must be moving in the negative direction. At the beginning, the shear is 0, so we start with 0 slope. But as I go to the right, it becomes faster and faster and faster negative. So I must be moving in the negative direction, like this. And how much will I lose? How much moment I will lose? The area under the shear diagram, which is 40 times 4 over 2, I will end up at minus 80. So this is negative, this is positive, okay? So what is the expression for the moment here in this case? The expression is the starting value, which was 0, minus the integral of this, which is minus 5x squared. So you see now, I get 3 different moment diagrams. Now, what do these moment diagrams have in common? These diagrams, they look all different, really, but they look only different in the constant and in the linear term. The constant here was minus 80, here it was 0, here it was 0. The linear term here was 20, here it was 40x, here there was no linear term. But, besides the constant and linear term, everything else beyond that is the same, right? The three different moment diagrams we got here, they look the same except of the constant and the linear term. All right? Is that clear? So we are going to see why this is very important and how this can help. I will talk about this next time. One more time. Please write this